island or something.
Thanks, Bill. Thank you, Bill. Let me introduce the next speaker, Dr. Peipei Ping, who is a professor of physiology, medicine, cardiology, and bioinformatics, and director of the NIH BD2K Center of Excellence at UCLA. Thanks for talking to us today, Dr. Ping, about regulatory principles of cardiac proteins on a global scale. Thank you.
Thank you. That's a nice introduction. And thank you, Jay, very much for inviting me. I appreciate the opportunity to share with you some of the progress we have made in the BD2K Center on data science in cardiovascular biology medicine. I apologize, didn't update the title slides. So in the past 10 years, my laboratory began first a quantitative approach to study cardiac proteomes, the proteins and their post-translational modifications in the setting of cardiac disease phenotypes. From that moment on, we recognized the need to build informatics platforms to characterize the large sets of proteomics data we have been collecting. That led to our first informatics-related publications that's relevant to cardiovascular medicine in CircRes, and too bad Roberto's not here. He really supported this line of research. And subsequently, through the efforts of about 6 undergrad students, and the lead was someone who was taking a gap year, we developed a 20,000-line Java codes to support first the quantification of protein half-life in the in vivo setting to study protein turnovers of mitochondria first and then subsequently other proteins. And then using the same strategy, apply it to isotope labeling of healthy humans and now with late-stage congestive heart failures to study protein kinetics in human settings, and subsequently a computational platform that automates this process and lead to singular biopsy sample prediction of protein half-lives from plasma samples of human beings. These 2 important projects in my laboratory that was developed over a span of 5 to 6 years from 2008 to 2003 led to the BD2K award and the subsequent actually work with this new investigator team. Several of them, you recognize the face. Primarily important, my collaborator, Professor Wei Wang at Computer Science Engineering School at UCLA, and Carol Watson in Cardiology Medicine at UCLA. And I also gave the amazing work that's done and acknowledgments for people in my own laboratory, Dr. Bilal Meraz, Dr. Harry Caulfield, and Dr. Ding Wang, who's sitting in the audience. So what we have received is, as many of you know, on the NIH Reporter, a very large sized NIH awards coming from the Common Fund Office of the Director, with awards from NIGMS to study big data concepts, analysis, and big data to knowledge workflows in cardiovascular medicine. And we're the only cardiovascular group awarded for this specific initiative. Throughout my career, I've dealt with program projects, I've dealt with contracts awards, but never of this magnitude of oversight from NIH. It's quarterly meetings, face-to-face, and weekly conference calls. For those of you who missed me at a couple of meetings at Great Wall Cardiology or OCC, you've all wondered where I was. And I can assure you, with no discrimination, my mother, my husband, and my dogs all asked the same questions. And I did work very hard, so it wasn't like I was goofing off. And I'm happy at this meeting to give you a progress of where we have been and what we have accomplished in the past almost 4 years now. So what have we done with the money? The one overall goal, arching goal, that our center has established is to design, develop, and deploy an integrated computational platform that provides investigators with easy access to large-scale data sets, the proper software tools to analyze them, and the annotations to interpret them. I took this off the abstract of my NIH awards. We then subsequently divided this task into 3 major aims, as recognized here in the slides as access and identify, process and analyze, annotate, and integrate. And specifically, what we have done in my close understanding of biology in cardiovascular research is build a number of user case supported workflows that directed as 2 types of data sets. One is structured data sets. Most of us commonly know, in my case, protein data sets and metabolite data sets, using machine learning-based algorithms to extract phenotypes and signatures and to develop a better understanding of these phenotypes. Second, again, is to understand another set of data sets, what we commonly call as unstructured data sets, that including both text data sets and imaging data sets. In my case, it's text data sets only. For sake of time, I'm not going to go into the reports and the analysis of how data sets and the nature of that it will grow in the next 10 years. But most commonly recognized is the growth are rapid and humongous in all types of data sets, but in particularly text data sets, it's going to represent more than 80% of biomedical data sets 10 years later. So in this case, text data sets including, for example, published records on Google Scholars, publications on PubMed, and any other text-based data sets, also including clinical case reports published, as well as clinical case reports just distributed, or ultimately EHR. This is the part of the next 10 minutes I'm going to focus on, as probably some of you already heard my talk in the first set of workflow we have developed. 5 minutes, okay. You heard the word machine learning a couple of times now from the last slides, and this definitely is an era where machine learning has been celebrated with the collaboration of both computer science and human being, as what Jay's symposium here signifies, the collaboration of engineering and medicine. If we could ever get this published, thanks to Joe and Roberto, is our overview on various different machine learning approaches and how that would address different kind of data sets in cardiovascular medicine. In particular, is how would they appropriately address, in this case, text data sets. Most of the algorithm we have developed is use this subcategory of machine learning called deep learning. And I won't go into details without time permission. I want to give you a specific, actually a true story use case. An investigator team, actually my own laboratory, want to investigate the molecular players in key mitochondrial pathways in different disease settings. An initial query of PubMed, which has one of the largest text data sets, using keywords mitochondria and proteins, returns over 100,000 publications. And using mitochondrial disease returns almost 40,000 publications. If we have a graduate student, a postdoc, or junior faculty member study each of these reports, assuming 4 hours is required to complete the study, and we would need at least 3 of them to work 12 hours a day, 5 days a week, 50 weeks a year, and that would still take over 60 years for them to complete this task. So the remark from my grad students is crystal clear: no way. And the remark from the junior faculty member is more dedicated. He said, we could give it a try and get it started. And I have a grad student who's a joint student in programs of bioengineering, where Dr. Song Li, who's a chair sitting in the audience, and the medical school is more smart. She said, perhaps we can get some help. And that's exactly what we're aiming to do. So eventually, to be able to effectively understand the data and the relationships of proteins and molecules and diseases embedded in the vast majority of publication, which is something all of us do, requires a set of data science solutions. That is text mining, data annotation, characterization, and integration of these data sets. So what we have done is to realize 4 major benefits of text mining through our platform, that achieving a better efficiency beyond human power in extracting information, achieving better accuracy and consistency in reviewing massive amount of publications, enabling discovery of hidden relationships that could have been overlooked by human manual curations, as well as applying and developing deep learning approaches to memory knowledge acquisition through a longer period of time. Imagine once you have done a set of studies that you come up with a review document. It doesn't have to say review was published in 2015. Thinking of it as a live document, you can automate the updates in a much more sufficient and efficient manner, and that's what this is. Algorithms carries memory and deep learning abilities to automate search through a web crawler that constantly grabs information of your own interest and coming together as the backyard supporting your research. So I'm going to skip some of the slides. The basic workflow we're currently building includes corpus generation, information document extraction, as well as effective organization of text phrases through multiple approaches. And I'm giving you a basic example today of what we've started to collaborate with a number of investigators, and with some initial results that supporting Mary Lindsay's special issue on extracellular matrix proteins. So what we've done is essentially NLP process and pattern recognition on different sets of variables. In this case, our variables are the major cardiovascular diseases and extracellular proteins. We've explored the application of phrase mining and network embedding on these textual data sets to reveal the relevant information, identities, and novel patterns of classifications, and eventually facilitate the predictive ability to gain novel mechanistic insights in these settings. I'm not going to go into details, but the basic technology we have created use a backbone technology that was used in the military, decoding much more complex messages and signals, what we call is K-SOLE. And using that information, we've been able to effectively decode and identify information in large quantity of publications. In this case, for Mary's projects, what we have done is to extract information from over 17 million publications and abstracts that's relevant to cardiovascular disease, that's over 1 million, as well as integrate inputs from both UniProt and extrametric cellular protein databases, and then create a case-OLE algorithm calculation for each and singular publication, as well as the relevant molecules designation to these 6 different disease settings. So without going into details, I can give you just a glimpse of what happens. The text data is very similar to the other digital number omics data or functional data all of us are familiar with. You could extract molecular signatures. You could then designate different groups of molecules belong to different disease and how the molecules separate these disease settings by principal component analysis that many of us in the audience do. And you can appreciate in this setting that for ischemic heart disease and the congenital heart disease, they're the most separable by extracellular matrix proteins. That's actually an outcome it was not expected. And if you go into details, try to understand better of the data sets, looking at the variations and the variance of directions of the vectors where the PCA are directed to, you could further appreciate the separation of the ECAM proteins in the 6 major disease categories. So I'm going to conclude. I have more slides. Happy to answer questions in the break. We have devised at this moment a natural language processing approach to annotate vast amount of text data. It can be used for cardiovascular disease or other diseases. It can be designated to any kind of variables you wish to, where I demonstrated to you 6 variables of cardiovascular diseases, more than 700 extracellular matrix proteins. The combination of the approach is freeze mining algorithm and a large-scale network embedding technique. They are fairly effective in recognizing patterns and differentiating relationships. To close, I think we have entered a different concepts of biomedical research, as what Jay said in his opening remarks. I think this is a wonderful time where engineering approach and computer science approach can be here in collaboration with all of us who have had our career in biomedical science. These are wonderful tools that could help us to better understand hidden relationships, to better understand mechanistic insights that we're all looking for. And I appreciate and welcome that we've entered this computer, machine, and human collaboration era. Thank you.
Okay, if Jay can come up and get set up while Peipei takes a question from the audience. Questions? Okay, in the interest of time, we'll move on then. So the next speaker in this venue needs no introduction, but I'll introduce him anyway. Professor Jay Zhang is chair of the Department of Biomedical Engineering here and one of our hosts. And so we look forward to his presentation on remuscularization of injured ventricle has been achieved in rodents. What's next?
So I will take the opportunity to report to you that in the next 15 minutes, what we are going to do use your money for the next 7 years. So as many of you know that we are founded by this PCTC hub, and we are the collaborator are the UAB investigators, Wisconsin Madison and Duke. You'll hear more from Tim Camp and Nina Bosak. And I want to convey that Danny Buxton want to continue to have this Jumpstart collaborating grant. So the main goal is to maintain the community together. So we have PCBC 7 years, and I'm very happy to see that the PCBC community continue and expand. And going forward, we'll have the community from the collaborator from not only United States, from Canada, from the Europe, from the Japan. We have the Doc Sawa's group giving the talk tomorrow also. So it is very exciting to see really the science and the engineering convergence, what it brings to us. So I was